Hey folks, how's it going? Mr. Mitchell here. In this video we're going to go over describing the motion of an object from a velocity time graph. So let's get started. So to kick off velocity time graphs, it says here that velocity time graphs can be used to represent the motion of objects travelling in straight lines. Some cases might involve objects starting from rest, i.e. stationary, or objects coming to rest. And we're going to look at how to describe the motion of an object from a velocity time graph based on lots of different cases. So the first case we'll look at is constant velocity. So what does it look like on a velocity time graph if an object is moving at constant velocity? Well, it says that a horizontal line on a velocity time graph represents a constant velocity, and that is shown by this diagram here. So we've got velocity on the y-axis, time on the x-axis, and you can see we've got a straight horizontal line which shows us that velocity is staying the same over time. So that represents a constant velocity. And I'm just going to show you a simulation to prove why it looks like this. So we're going to use some software called Motion Tracker, which is going to let us track the motion of this object. So we've got a car here, and if we click play, you'll see it's moving at a constant velocity. And we're going to step the motion forward in intervals of 0.5 seconds, and we're going to track where the vehicle is. So if I put a marker at the front of the vehicle there to start us off, I'm then going to step the motion in 0.5 seconds along, and I'm going to put another marker there, step the motion again, put another marker, and keep going until we get to the end. And you'll see over on the right hand side, the graph that I'm interested in for velocity time graphs is this one in the middle, the velocity versus time graph. So if I fit a gradient to this line, you'll hopefully see it traces out roughly a straight horizontal line. And that's showing us that the velocity is remaining the same over time, i.e. a constant velocity. And another thing to notice here is that the distance the car travelled between each of these 0.5 second intervals was the same each time. So at constant velocity, the car should travel the same distance in that given time. Going back to the notes now, we have uniform acceleration, also known as constant acceleration. So it says that a positively sloping line on a velocity time graph represents a uniform or constant acceleration. So here we have our VT graph, and we've got a straight line with a positive gradient. It then says the steeper the slope of the line, the greater the acceleration. So in the example below, object X has a greater uniform acceleration than object Y, and that's because object X is steeper than object Y, i.e. X has a more positive gradient than Y, so it's going to have a greater acceleration. So both still show constant or uniform accelerations, but it's just that X has a greater value of acceleration than Y. Again, I'm just going to show you a quick simulation using the tracker software. So this time if I click play, you'll see the car accelerate from rest, and that should be a constant or uniform acceleration. So we're going to do the same as what we did for constant velocity, and we're going to track along the motion of the vehicle in steps of 0.5 seconds. So if I put my marker at the front again, and then step the motion forward, you should see over on the right hand side, remember we're only interested in the middle graph here, velocity versus time, and you'll see we've got a positively sloping gradient if I was to display this gradient line on the graph. So something like that for a line of best fit through the points shows that I've got a positively sloping gradient. And another thing to notice is that the distance between the pairs of markers here increases as the car gains speed. And that's because if the car is accelerating uniformly, we should expect it to travel a greater distance between each of the 0.5 second segments. This time, jumping back to the notes, we have uniform deceleration. And it says that a negatively sloping line on a velocity time graph represents a uniform or constant deceleration. So remember, deceleration is just a negative acceleration, which means that an object is slowing down. So here we have our graph for a deceleration, so our velocity against time shows a negatively sloping line on the graph. And I'll just show you the motion grapher for this one as well. So this time if I click play, you'll see the car is moving to begin with, and then it decelerates to a stop. So just like before, we're going to track the motion of the object, and you can pay attention to this graph in the middle here on the right hand side. So I'll just track the front of the car again. So if I step the motion along in steps of 0.5 second intervals, this is what we get. Okay, and if we look at the right hand side again, the velocity versus time graph in the middle, you'll see that we have a negatively sloping line. So if I fit the gradient to that, a line of best fit, you'll see that we get this kind of negatively sloping line like that, with a gradient value of negative at 3.5 this time. So we should expect for a uniform or constant deceleration a negatively sloping line on a velocity time graph. And it's also worth pointing out that the distance between the markers, i.e. the distance travelled by the car over time at intervals of 0.5 seconds, decreases as the car slows down, which is telling us that the car is decelerating, i.e. it covers a shorter distance in the same time as the vehicle slows down. Our last case now is to look at motion in the opposite direction, i.e. what happens when an object is moving one way and then it changes direction and travels back in the way it came. So this could be like a car travelling in one direction and then it starts reversing back in the same direction it came. Or it could be a ball thrown upwards into the air and then the ball travels back downwards towards the ground. So it says here that as velocity is a vector quantity, a negative value indicates motion in the opposite direction. So in the example below, the object decelerates uniformly to rest before accelerating uniformly in the opposite direction. This is in fact the velocity time graph for a ball that has been thrown upwards into the air and then travels back down towards the ground. So if we look here, we've got our velocity time graph and we've got positive velocities above the x-axis and negative velocities below the x-axis. And you'll see that we start off at a non-zero value of velocity, and that suggests that the ball is thrown into the air at some non-zero value of velocity, say 10 meters per second for example. And as soon as that ball leaves the person's hand at 10 meters per second, it's going to start slowing down as it reaches its highest point in motion. And once it reaches the highest point in motion, it's going to come to a stop before it then travels back down towards the ground. So we could say that the object is at rest at this point at its highest point in motion. And then what we're saying is that in order to show a change in direction for the object, to show it's going to go back in the opposite direction to the original motion, then we need to show it changing from one side of the x-axis to the other. So in this case, because we started off with positive velocity, we're going to need to move into the negative region below the x-axis. So we're showing a change in direction at this point because we've gone below the x-axis, and that means the ball is no longer travelling upwards, it's now started travelling back down the way after it's been at rest. And at this point down here, the object may return to the thrower's hand, or it just might hit the ground, for example. So the main thing to be aware of here is that we've gone from positive velocity to negative velocity to show a change in direction. And I'm just going to show you a quick simulation to help you visualize this. So here we're back to our motion tracking software, and if I click play, you see the ball travels upwards and back down the way. So we've got a ball thrown into the air, which is going to travel back down. And this time we've got a time interval of 0.15 seconds between the markers. So I'm just going to track the motion by putting markers on like we've done for the other cases. So remember, these are steps of 0.15 second intervals. So track it until the ball gets to its highest point there, and then it starts travelling back down the way. Now notice, right now what I've got is a negatively sloping line on my velocity time graph, and that is, remember, because the ball is thrown with a non-zero value of velocity up here, say 5 meters per second in this case, and then the ball is going to slow down as soon as it leaves your hand until it reaches its highest point. And you can see that the ball is covering a smaller distance each time between the markers in the same time of 0.15 seconds because it's slowing down. However, the ball is now travelling in the opposite direction, and as soon as I start tracking this motion, we should see the data points on our graph now appear below the x-axis because we want to show a change in direction on the graph, and we can do that by going from positive velocity to negative velocity. So if I track here, you'll see we get a point below the x-axis, and then stepping the motion, we should see more points below the x-axis. Okay, so here we've got the graph that we expect, the one for the ball thrown upwards into the air that's then going to fall back downwards. And I can then fit a gradient to this to show you that it's a negative gradient and all the points fit roughly on a straight line. So we've got a negative gradient value here. Another simulation here shows how to combine some of these cases that we've looked at. So here we've got a car, and I want you to pay attention to the speed time graph shown here. So if we accelerate first of all, then you'll see a positively sloping line on the graph. And let's say we get up to 40 miles per hour. And let's say I leave it there, then the car is going to travel at a constant velocity. And you see we've got this straight line now on the speed time graph. And then as soon as I brake and bring the speed down, let's say to about 20 miles per hour, then when we were braking, i.e. slowing down, we got a negatively sloping line on the speed time graph. And then again, I've stopped accelerating or decelerating, so the car is again travelling at constant velocity. And let's say I now brake so the object comes to rest. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.